Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part one of the transportation segment. Transportation is probably the most important example of energy use in our society. In part one, we will discuss cars and energy, efficiency of combustion engines, and electrical cars.
Let's talk about cars. In this part, we will discuss how much energy does it cost to drive a car, where does the energy go, and we will discuss electrical cars. Let's discuss first how much energy cars use. The Environmental Protection Agency estimates that each vehicle drives about 12,000 miles per year. So if we assume that most of these miles are driven with one person in the car, then that would mean that each of these drivers drives about 33 miles per day. The EPA furthermore estimates an average fuel consumption of 20.3 miles to the gallon. These 33 miles would turn into 1.6 gallons of fuel that would go through the car every day. The energy in 1 gallon of gasoline is 36.1 kilowatt hours, and so that would bring us to 58.7 kilowatt hours per day and car. It's interesting to calculate the average power needed to provide this level of energy. So if we would power cars continuously throughout the day, then we would need a power plant that can provide 2.4 kilowatts to provide energy to one of those cars. So it's interesting to compare this number with the 1.25 kilowatts of electrical power that we need per average house. If you think of the efficiency of electrical power plants for converting fossil fuel to electrical energy, that is about 30 to 60% depending on how advanced that power plant is. These 1.25 kilowatts actually turn into a fairly similar amount of fossil fuel like the 2.4 kilowatts that we just calculated for the average car. So what that means is that if you live in a house and you drive your car, half of the energy that you use goes to the house and the other half goes to the car. If you have a typical situation that there are several cars per house, the house almost becomes an afterthought in the energy total of the inhabitants of that house. Another interesting thing to consider is if we assume that all cars are electrical, we can estimate how many more power plants we would need in the US to provide the electrical power to all these cars. So the 2.4 kilowatts here, that's the fossil fuel power that goes into the car. If we assume an average engine efficiency of 25%, that would mean that if we would drive this car electrical and we would have the electrical energy readily available without losses, then that would be about 0.6 kilowatts, a quarter of this here in electrical power. Now here, of course, we assume a 100% efficient electrical motor, but they're pretty close to that. So if each car would use this here, 0.6 kilowatt hours in electrical power, and we provide that power with a power plant, we would need to estimate that we lose about 20% of the power during transport through the high voltage lines and in the battery storage in the car. And so that would mean that we need 25% more energy than the 0.6 kilowatts can provide, and that takes us then to 0.75 kilowatts. So this is basically what we need from the power plant. So if we assume we have 180 million drivers, and it's pretty much the same number of cars that are in the US, we can calculate that this would need about 135 additional 1 gigawatt power plants. So if we switch to completely electrical vehicles, then we would have to build another 135 additional major 1 gigawatt power plants throughout the US. Another interesting question is how much energy does a car use per distance? We want to do this here in metric units, so we need to convert the 20.3 miles to the gallon number from the EPA. So a mile is 1.6 kilometers and a gallon is about 3.8 liters, and so we get here 20.3 times 1.6 divided by 3.8, and that gives us 8.5 kilometers per liter. Then we can calculate liters per 100 kilometers, and that takes us to 11.76. So the energy in 1 liter of gasoline is about a quarter of that what's in a gallon, so we get 9.5 kilowatt hours. We can calculate based on the 11.76 liters per 100 kilometers that we need 111.72 kilowatt hours per 100 kilometers. In other words, a 1000 kilometer or 600 miles road trip would consume approximately the energy that an average house would use per month. It's interesting to see how the United States compare with the rest of the world in terms of average miles per gallon. Here's an interesting graph. It shows the year down here. So, of course, this graph is from 2007. So there are certain projections. The y-axis is the miles per gallon converted to a CAFE test cycle. So CAFE test cycle, that's the corporate average fuel economy test procedure. So these numbers are a little bit different apparently than the EPA numbers, but we can easily compare the ratios between the different regions in the world. And so what we see on this graph are the curves for Europe, for Japan, for China, Australia, South Korea, Canada, United States, and California, which is a little bit the trendsetter for the United States. And so what we see here is that the United States is definitely the world leader in fuel consumption, right? All the other countries apparently get better miles per gallon, led by Europe, which is here at about 40. That corresponds to about 6 liters per 100 kilometers. And they are planning to cross the 50 miles per gallon line in the near future. In the US, we also have an upwards trend, a little bit stronger in California, but there's still a long way to catch up. And really the main reason for our poor miles per gallon performance are that we use big vehicles. A large number of SUVs and trucks, light trucks on the road, that lowers the average miles per gallon considerably. In Europe, smaller cars are much more prevalent, so that's the main reason why they have a much better miles per gallon number. We know now that cars use a lot of energy comparable to houses. Now in the next few slides we will look into where does this energy go. You know now that all heat-based engines radiate a considerable amount of heat away in order to generate useful work. In cars, this is about 75%. So these 75% of the energy, of the fossil fuel energy, is just radiated away in the radiator into the low temperature reservoir, which is the air surrounding the car. And then the 25% is converted to work that actually hits the wheels. These 25%, they provide acceleration of the mass of the car. Of course, when you stop the car, then this energy, this kinetic energy, is also converted fully to heat. And as the car moves through the air that surrounds it, there is air resistance. In effect, we're heating up the air around the car, and then there's also rolling resistance, which summarizes all the friction-related energy costs. Let's look into these energy quantities a bit more in detail. Here on this slide, the energy used for acceleration is discussed. So assume you drive around in the city and you are between stop signs. Every time you stop, you have to accelerate the car again, and then you stop the next time and the car comes to a full stop. Let's say the distance between these two stops is d, and you accelerate the car to a velocity v between the stops. After you accelerate it, it has a certain amount of kinetic energy, and the formula for this kinetic energy is 1/2 times the mass of the car times the velocity squared, and that's the velocity that you reach after the acceleration is complete. This energy, 1/2 mv squared, that is fully lost the next time you brake at the next stop sign or red light. The shorter the distance between, the larger the entire amount of energy that is being used per distance. So we divide by the distance d between the two stops. And so in the end we have a formula where we have 1/2 the mass of the car divided by the distance times the velocity square. Now, when you drive around, there is not much you can do about the distance, right? The stop signs, they are where they are, and you have to stop there, otherwise you'll get a ticket. The only two things we can control is the mass of the car and the velocity. The energy depends on the square of the velocity and linearly on the mass of the car. So if you have a lighter car, or you don't drive so fast in between the stop signs, then you can lower dramatically the amount of kinetic energy that you need to put into the car, and of course that will cost less fuel. Acceleration is not the only energy cost in cars. As we move the car forward, it has to go through the surrounding air. That causes a cylinder of swirling air around the car. The cylinder has a cross-section that is proportional to the cross-section of the car. The length is defined by the distance that we're driving, and the velocity that we impart on the air mass that is in the cylinder, that is the same as the velocity of the car. So all we have to do now is calculate the mass of the air that we accelerated to velocity v, and then we can calculate the kinetic energy that we put into the air, and of course that kinetic energy came out of the gas tank of the car. So this is the energy loss to air resistance. Now, how can we calculate the mass of the air in this tube? What we need here is the density of the air and then the volume of the cylinder. And the volume is calculated by the length times the cross-section. Now, this cross-section that scales with the cross-section of the car with a proportionality factor called the drag coefficient. That is defined by the degree of aerodynamic design of the car. Modern cars have about 0.3. The effective cross-section of that air tube that we are swirling around is 1/3 approximately of the cross-section of the car. And so we calculate the mass of the air is the density of the air times the length times the cross-section. And so we end up with the standard kinetic energy formula, which is 1/2 times the mass times the velocity squared. And here for the mass we have the mass of the air that is in that cylinder of air that is being swirled by the car. So we see again that the kinetic energy cost depends on the velocity of the car, goes quadratically, and it also depends on the distance that we're driving. So there are two ways we can, or really three ways we can influence this. We can make the cross-section of the car smaller, so more aerodynamic design. We can drive less, reduce the distance, or we can go at a lower velocity. This of course is a really big impact because it goes quadratically with the velocity. Here's a list of typical drag coefficients. We start out with a truck, which is essentially a brick that moves through the air. That's 0.6. A Hummer H2 is pretty close to that, 0.57. And then we go down through light trucks, 0.39 to recent cars that are optimized, 0.25. I also put here a cyclist on there. It's 0.9, so this is actually really bad, and that makes sense because the human body is not really very aerodynamic. On the picture, that's an interesting footnote of history. That's the General Motors EV1, one of the first fully electrical cars. That had a drag coefficient of 0.19, which is pretty impressive, but you see it has a very slippery aerodynamic shape. Now keep in mind that the drag coefficient is not everything. The actual cross-section of the car also plays a role. So drag coefficient times cross-section of the car defines the cross-sectional area of the air cylinder in which we accelerate the air. It's interesting to compare bicycles and cars in terms of air drag energy cost. We use the formula for air drag energy cost per distance. It's 1/2 times the density of the air times the cross-sectional area. That includes the drag coefficient times the velocity squared. We compare a car that goes 100 kilometers per hour, that's 60 miles per hour, or 27.7 meters per second, with a bike that is going at 20 kilometers per hour. That's a fairly comfortable speed for somebody who is not entirely out of shape, and that's 5.5 meters per second. The drag coefficients are 0.33 for the car and 0.9 for the bike, and we assume a cross-sectional area of 3 square meters for the car and 0.75 square meters for the bicycle. Air density is 1.3 kilo per cubic meter. And we also assume that the efficiency of the engine and human body is about 25%. Okay, so the air drag energy cost for the car, we can plug in the numbers now here into the formula. We get 493.8 joules per meter. And for the bicycle, we get 13.3 joules per meter. So this is about a factor 37 between the two. That means that the bike needs about 2.6% of the work to be pushed forward against the air drag than that the car needs. The main difference for that is, of course, the much slower velocity of the bike, and there you see the importance of the velocity in this entire consideration, because it is going quadratically with the velocity. So reducing the speed by a factor half gives you a factor 4 in energy savings. Okay, so if we calculate now the energy to travel 20 kilometers at these constant speeds, so that's 20,000 meters, and so we multiply 20,000 with that number joules per meter and times 4 because of the efficiency 25%. We need a fossil fuel input of 39.6 megajoules, which is 11 kilowatt hours. The bike, we do the same calculations with the bike energy per meter, and there we get 0.29 kilowatt hours. So if you compare it with the energy in a Snickers bar, standard size, which is 271 kilocalories, which can be translated into 0.31 kilowatt hours, that means you can basically, with the bicycle, you can travel 20 kilometers just on one single Snickers bar. Pretty impressive, but also, of course, sobering, because if you eat one too many, you have to go quite far to work it off on your bicycle. But there's no question that shifting some travel from cars to bicycles would result in a tremendous energy savings, even if the bicycle were powered electrically. Now let's discuss rolling resistance. That's the second energy drain when you drive a vehicle. This basically summarizes all the energy loss due to friction because of the rolling process. So it's the interaction between the tires and the pavement and the friction that is in the axles and so forth. And it's interesting to calculate when is the rolling resistance equal to the air drag. What is the velocity at which both are the same? And so we do that by equating the rolling resistance with the air drag. And that's what we have here. So this is the air drag formula from the previous slides, and this here is the rolling resistance formula, which is essentially just the rolling resistance coefficient, CRR, times m times the gravitational force. So this is just the force normal to the ground. And so if we equate this with the air drag and we put these numbers in here for a car, a really small light car, 1,000 kilograms, that may be a Volkswagen Polo or something of that nature, then we assume a typical rolling coefficient of 0.01 and a cross-sectional area of 3 square meters and a drag coefficient of 0.33 and an air density of 1.3 kilograms per cubic meter. Then we can solve this equation for the velocity and plug in these numbers, and so we end up with 44.7 kilometers per hour. That's about 30 miles per hour. So at that speed, the air drag becomes the dominant energy drain when driving any vehicle. So when you go on the freeway at 60 or 70 miles per hour, because the velocity is squared in the formula for the air drag, that means that the rolling resistance is negligible. Most of the energy goes into combating air drag. Here now we compare the energy consumption per 100 kilometers and per person for cars, bikes, and also trains. And we have down here the speed, and on the y-axis we have the energy consumption in kilowatts per 100 kilometers. For the train it is per 100 person kilometers, because many people share the train. And what we see is that the scale for the car is vastly larger than for the train. We have about here this ends at 2 kilowatt hours per 100 person kilometers, and here we have 100 kilowatt hours per 100 kilometers. So the car is vastly more inefficient than the train when it comes to person kilometers. And the reason for that, of course, is that the car is a big heavy vessel in which that just one driver sits, while on the train many people sit behind that cross-sectional area that defines the train drag. That's the reason why per person trains have a really very low energy consumption. Furthermore, trains have the best rolling resistance. If you look at the scale here, they are below 0.5, while the bike is at 0.5, and you see here that the rolling resistance coefficient of the bike is more than 2 times that of the train. And cars, if you ever pushed one, you know that it's pretty difficult to push a car forward, so the rolling resistance coefficient is 0.01. Now that of course also has to do with the weight if you push a car. So it's pretty obvious that using trains has a vast advantage over using cars in terms of energy consumption per 100 kilometers. But of course, one needs to keep in mind here that for trains, this benefit can only be realized if the trains are full of people. If a train is mostly empty, it can get pretty energy intensive to transport people. But that's the same for all public transportation schemes. They only work if they are popular and many people are using them. The previous slide seems to suggest that going slower always leads to lower energy consumption. But of course, this is not true with real cars that have transmissions and combustion engines. If one measures the energy consumption, here it's at the example of a BMW 318, it turns out that below a certain velocity, because the car essentially needs to be downshifted, so the engine runs at higher RPM, the energy consumption goes up again. So for each car there is actually an optimum speed, which is around 60 kilometers per hour, which is close to 40 miles per hour. At that speed, most cars are in the highest gear, and so the engine turns at the lowest RPM and at the highest output per stroke. That typically means that the engine runs more efficiently than when it goes at higher RPMs but lower per stroke output. A hybrid car like the Prius can beat that because it can switch to electrical propulsion at low velocities, and so it can realize the benefit of going even slower. Here's an interesting comparison between a BMW 520 diesel and a Prius with a gasoline-electric hybrid drive. With this we want to start our journey into the efficiency of combustion engines. And so we see here that over 545 imperial miles, which translates into 452 US miles, that's the distance from London to Geneva, they drove that distance with both cars. What they found is that the Prius had a slightly worse mile per gallon outcome than the BMW. The BMW clocked in at 41.8 miles per gallon, and the Prius had 39.9 miles per gallon. And so while this seems to tell us that the Fahrvergnügen wins here over the Prius, this is of course not the entire story. While the BMW has a better miles per gallon number, we need to take into account here that it has a diesel engine. Diesel fuel has a 10% higher energy density per volume. That means that this BMW actually used 10% more energy than we think it did in comparison to the gasoline engine of the Prius. This additional energy comes, of course, from a higher hydrocarbon content of that volume of diesel, and that means that the BMW also emitted more carbon dioxide than the gallons would suggest. So we're a little bit comparing apples to oranges in this case. Another thing to take into account is that turbo diesel engines, or diesel engines in general, have a higher efficiency because the fuel-air mixture can be more highly compressed, which gives these engines a higher conversion efficiency compared to gasoline engines. So we have a lot of factors that need to be taken into account when evaluating this comparison. The Prius wasn't able to use its regenerative brakes that much in this test because it was mainly freeway and highway driving and not so much city driving, right? The regenerative braking can recoup about 50% of the energy that is wasted during deacceleration, and the BMW has the advantage of a more efficient engine, which of course is shining in this test because most of the driving is on freeways and highways where a lot of work has to be done against the air drag. That is where a turbo diesel engine is really an advantage. So what did we learn from this test? Well, it is very difficult to really compare between different technologies. Here, the hybrid gasoline engine and the diesel engine. We also learned that one needs to really look into the boundary conditions of such tests in order to understand the outcome. Now I want to discuss the efficiency of combustion engines. In a combustion engine, we always have a piston and a combustion chamber in which a gas is brought to a certain pressure, and then this gas is able to push this piston out, and during that process work is being performed to the outside of the system. So we're transferring energy from the gas to the outside via this work that is performed by the piston. If we want to calculate the amount of work that is coming out of this system during the motion of the piston from position 1 to position 2, we need to look into the change of total kinetic energy of this gas. If you remember the ideal gas law, we know now that pressure times volume is equal to the energy that is in the gas. So essentially what we need to do is we need to compare the energy that's in the gas at point 1 with the energy that's in the gas at point 2, and the difference of these two energies, that's essentially the work that came out of the system if we assume that no energy exchange occurred through heat. So that means that this is perfectly insulated. That is of course a theoretical condition that in the real world could not be achieved. So this here will give us the maximum of the work, the theoretical maximum that can come out of this process. So in a pressure volume diagram, this process of having high pressure in the beginning and then pushing out the piston to a second position at a larger volume, that corresponds to this process path. So the gas inside the combustion chamber that follows this process path, so the pressure goes down and the volume increases during this process. So if we want to calculate the work that comes out, we need to calculate the energy here and the energy there and subtract them. And so this is essentially done with an integral. So we integrate from volume 1 to volume 2 over the pressure, over this curve, and that gives us essentially the area underneath the curve. And this area is the energy change of the system, and if no heat is being exchanged, that is the work that came out of the system. Let's look at the efficiency of an Otto-style car engine. This is the car engine that is most popular. It's also known as the four-stroke engine. The first stroke, we compress the air-fuel mixture. That means the piston moves up to the top dead center TDC position. Then the spark occurs, and that increases the pressure up here as the fuel-air mixture combusts, and that pushes the piston down. This is called the power stroke or the expansion stroke. That's the stroke during which work is being performed on the outside of the system. Energy is coming out of the system. Then once the power stroke is over, we need to exhaust the spent air-fuel mixture. That's done during the exhaust stroke. So just by inertia of the engine, the piston is pushed up and the gas is exhausted through the exhaust valve. In the final fourth stroke, the fresh air-fuel mixture is being sucked back into the combustion chamber as the piston goes down. And then we arrive back here at the beginning, and we can again compress and expand, and that starts the next cycle. In the pressure volume diagram, this process follows the path shown here. The compression stroke starts here. The air-fuel mixture is being compressed to the ignition point. So this is when work is being actually put into the system. Then the explosion occurs and the pressure rises at constant volume. Right, the piston is already at the top dead center position. It doesn't go anywhere, but we get the explosion and the pressure rises because of the rise in temperature. And then the expansion starts. The piston is being pushed out and work is performed on the crankshaft. So this brings us essentially to this point. The piston is now back down. And then we go into the exhaust stroke and then the intake stroke. So essentially here there is, if there's no friction or anything, there is no work performed in either direction, but in real terms, of course, because overpressure builds up here to get the gas out and we create vacuum to suck the air-fuel mixture in. There is also, of course, some work performed, plus there is in a real engine, of course, friction during this cycle. So this costs some of the energy that is coming out of the expansion stroke. But essentially, the work that is being performed by the system is now the work that came out of the expansion minus the work that it costs to compress. And so what we need to do is we calculate the integral of this curve and then subtract the integral of this curve, and that gives us the area that is within this loop. And that is essentially the work that is being performed by the Otto engine during its power cycle. Now we're ready to understand why diesel engines are more efficient. On the last slide we discussed the standard gasoline combustion engine, the Otto engine. In these engines we start out with a cylinder filled with a fuel-air mixture that is compressed. So we put some work into the system, the pressure increased to 0.2 and the piston is at the top dead center position, so all the way up. And then the spark plug ignites that mixture, the pressure rises, and we get the expansion stroke, the power stroke, during which work is performed. Then we exhaust the combustion chamber and get fresh air-fuel mixture in there, and then we compress it again and the cycle starts again. The work that is coming out of the system is the area that is enclosed by this process loop. Now in such an engine we can reach about a 1 to 12 compression ratio between 0.1 and 0.2. Now in a diesel engine we can actually go beyond this point. So the gasoline 0.2 would be here. However, we can compress further to a much higher 0.2, much higher pressure. So the compression ratio in a diesel engine can be 24 to 1, so twice as high. And this is possible because in that compression stroke we only compress air in a diesel engine. The gasoline, or the diesel rather, enters the combustion chamber after the air is compressed. So there is a high pressure fuel injector that injects the fuel into the already compressed air, and that leads to a self-combustion of the diesel air mixture, which then leads to an expansion. So the piston is already moved downwards while the diesel fuel is burning in the cylinder. And because diesel fuel burns much slower than gasoline because of the longer hydrocarbon chains that are in diesel fuel, the pressure stays roughly constant as the volume increases. So we get combustion and volume increase at the same time between points 2 and 3, and the pressure stays more or less constant. Then at point 3, after the combustion is complete, we go through the standard expansion cycle that performs some more work. So what we get is, in a diesel engine we have the standard gasoline work output and an additional part here that is only possible because of the higher compression and the slow burn of the diesel fuel. And this is the added work output of a diesel engine, which increases its efficiency compared to a gasoline engine. In cars, this leads to an about 5% higher efficiency than for gasoline engines. Gasoline engines get about 25% and diesel engines have about 30% efficiency. Big diesel engines, like in ships, they can actually reach larger than 50% efficiencies, which brings them close to the latest generation of coal-fired or gas-fired electrical power plants. The other advantage of diesel fuel versus gasoline is that it has a higher energy density. This here is a graph from Wikipedia that compares various energy sources in terms of energy density per volume, so that's the y-axis, and energy density per weight, that is the x-axis. We see here that diesel has a maybe 10% higher density per volume, but it has the same density per weight. So that means that a gallon of diesel simply weighs 10% more, and we get 10% more hydrocarbons in there that can be burned. Therefore, a gallon of diesel fuel contains 10% more energy, which justifies the slightly higher price that we pay at the pump for diesel. This figure contains some more interesting information. If you look, for example, here at ethanol, ethanol has an about 30% lower energy density than gasoline or diesel. So that means when you buy gasoline that has ethanol mixed into it, you actually get less energy per volume of fuel that you're buying. Down here is the lithium-ion battery, and you see it is very close to the origin of this graph. That tells you that a lithium-ion battery has a very poor energy density in comparison to the usual fossil fuels. That is one of the biggest problems of electrical cars, because we need a much heavier and much bigger battery than a comparable gasoline tank for the same range of the vehicle. If you look over here at the far end of the energy density per weight scale, there we have liquid hydrogen and hydrogen gas. And so that tells us that hydrogen has a very high energy density per weight. However, it is problematic to get it in a form that we actually have an efficient size of the tank. So the energy density per volume is consistently low of hydrogen, which makes it difficult to store and to transport. So you see that the conventional liquid fossil fuels that we're using are in a fairly sweet spot. They have a very efficient density per volume and per mass, and this makes them so convenient. So an interesting question now is, why don't we just all drive diesels? We have a higher energy density, we have a higher efficiency of the engine. It sounds like diesel is really the solution. But if you look at the hydrocarbon contents in a barrel of crude oil, we have to realize that we get a mixture. This is why we need refineries to use crude oil in engines. In a refinery, fractional distillation is used to distill the components of crude oil into standardized fuel types. So here you see a schematic of a fractional distillation setup. The crude oil is heated up in a furnace and then put into this distillation column. Here we have various temperature regions, and in each of these temperature regions we can extract the components of crude oil. The higher we go in this column, the shorter the hydrocarbon chains are that are being extracted. So at the top end we get actually gas, then here we have naphtha, then gasoline, paraffin, then diesel, down here lubricating oil, and at the bottom we even get bitumen. Bitumen we know already from the Canadian tar sands. That's that gooey tar material that comes out of the ground there. This explains that in each barrel of crude oil we have a certain ratio of these different fuel types. So we can make 18.56 gallons of gasoline from that barrel, but only 10.31 gallons of diesel. This immediately suggests that we need a fleet of vehicles that have a balanced number of gasoline engines and diesel engines that match this ratio that is in the crude oil. It's immediately clear that only a third of the cars can be diesel cars, and the other 2/3 about need to be gasoline powered if we want to use the entire barrel of crude oil. Now I want to discuss electrical cars. You remember from the Energy Basics segment that one of the big advantages of electrical energy is that it is very high quality. And in electrical cars, once we have the electricity, the electrical energy, we can convert it to work with a very high efficiency. 80% is absolutely possible. That compares to 25% in an internal combustion engine. Now the problem is of course to generate the electricity, which at this point we are mainly generating with coal or gas. But there is a little advantage to that, because large-scale electricity production is more efficient than car engines, combustion engines. So we can easily get 50% with modern power plants. So that gives us a distinct advantage over converting the fossil fuel inside a combustion engine at 25%. However, we need to take into account transmission losses. The electricity has to get from the power plant to the battery of the car, and so we can easily lose 10 or more % in the grid, and that can reduce the efficiency to 33 to 40%, and so we're out of a sudden again much closer to the 25%. And then the batteries aren't 100% efficient either. It's easy to lose about 10% in a lithium-ion battery between charging and decharging. And so that takes us pretty close to the 25% of the combustion engine. It may still be a little bit better, and of course every % that we can squeeze out of this process counts. The real advantage with electrical cars is that regenerative braking is a natural for them, because an electric motor doubles as a generator, so one can fairly easily recoup 50% of the energy that is otherwise wasted to braking. Taking all this together, electrical cars definitely have advantages, but they are not a quantum leap at this point in terms of emissions reductions, because we are producing electricity from fossil fuels mainly. One of the most pressing issues of electric cars is their range. Because of the very low energy density of batteries, which is about 1% of fossil fuels, so that's 0.1 kilowatt hours per kilogram versus 10 kilowatt hours per kilogram in fossil fuels. This means that a significant part of the weight of an electric car is the battery. Only because of modern lithium-ion batteries that achieve that 1%, it has become possible to make electric cars that have a sizable range. This graph compares the energy transport cost in kilowatt hours per 100 kilometers for cars with lead-acid batteries and cars with lithium-ion batteries, the red curve, versus their range. So you see that with lead-acid batteries, which have a even lower energy density than the 1% of lithium-ion batteries, it is virtually impossible to reach a sizable range, because very quickly most of the energy that's in the battery is being used to actually transport the battery itself. So the payload goes down dramatically. With a lithium-ion battery, we achieve a much lower increase of this curve, so that larger ranges are possible, such in the Tesla cars that have 200-300 miles range, depending on the battery pack. But you still see here that even with lithium-ion batteries, the transport cost goes up significantly as the range increases, because of the strongly increasing weight of the battery. We're talking here hundreds of kilograms, and these estimations are done for a very light car. The energy transport cost actually goes up by about 30% between a car that has only 100 kilometer range and one that could go 500 kilometers. So that's pretty sizable. There's a lot of confusion about the energy efficiency of electric cars. Here is the EPA, the Environmental Protection Agency sticker for the Chevy Volt. And they say here that if you drive it all electric, so only with the battery and the range extender engine is off, then you reach an efficiency of 93 miles per gallon equivalent. Now, if you drive it just with the range extender engine, so after the battery has been exhausted and the range extender engine is on, it's just a regular gasoline engine, then you get 37 miles per gallon. And considering that the Volt is a fairly small car, 37 miles per gallon is quite average. There are plenty of small cars that actually have a better mileage. So the question really is, how can, just because we drive it with the electric motor, how can the efficiency go up about a factor 2.5, right? If you divide 93 by 37, you get 2.5. A hint what's going on is that they say it takes about 36 kilowatt hours per 100 miles. And if you remember, 36 kilowatt hours, that is just the energy that's in 1 gallon of gasoline. What's happening here appears that they simply say, okay, it takes 36 kilowatt hours to drive it 100 miles, electrical kilowatt hours, and that is equivalent to the energy that is in 1 gallon of gasoline, and so we end up with about 100 miles per gallon. So that's a pretty fantastic calculation. What they actually are doing is they are comparing the electrical energy, that is a very high quality energy, directly with the lower heating value of gasoline. And the lower heating value, that is essentially the energy that we could extract as heat from the fuel. So if we would just burn it, we would get 36 kilowatt hours of heat out of the fuel. But you know now from the energy basics segment that in any heat engine we're losing a sizable amount of this heat energy, and we only get a fraction of the heat energy out as work, which allows us to make electricity in a power plant. So as long as we generate electricity from fossil fuels, a rating like this is entirely questionable. Even if we assume 50% efficiency in a power plant and very minimal transmission losses and perfect batteries and perfect electric motors, we would still only get about 50 miles per gallon or 45 miles per gallon out of this process. This sticker is fairly misleading, and it compares apples with oranges. The only comparison that might make sense is actually to compare the CO2 emissions using average numbers for electrical power plants and compare that with the carbon dioxide that comes out of gasoline engines. That would really weigh the amount of fossil fuel that is being burnt for each mode of transportation, and that would give a clear comparison of the amount of hydrocarbons that went through the exhaust for the all-electric and the gas-only driving modes. Luckily, we do not have to use the EPA sticker if we want to assess whether it makes sense to drive an electrical vehicle compared to gasoline-powered vehicles. In 2015, the Union of Concerned Scientists put out a report that assessed the total lifetime emissions of electric vehicles in comparison to gasoline cars. They did that by taking into account the energy mix that is used in each of the electrical grids that we have in the United States. Here you see a map of their results. For each of the grids, they calculated the equivalent miles per gallon in terms of greenhouse gas emissions. So let's say you would live in California and you would have the average electrical car, then you would achieve greenhouse gas emissions that are equivalent to a gasoline car that would do 87 miles per gallon. If, on the other hand, you would live in Kansas and charge your car there, then you would just achieve 35 miles per gallon, which is not that different from a standard gasoline-powered car. So you see here, it makes a big difference where you live if an electrical vehicle makes sense or not at this point in time. What I just showed you was, of course, a snapshot in time in 2015. That's when the report was written. Things do get better over time, and we can assume that more and more power plants are being converted to less carbon-intensive fuels. Here you see how the composition of the grid changed over the years, and so you see that the renewables are definitely on the way up and that coal is on the way out and natural gas is going up. So we can expect that in the future the equivalent miles per gallons will improve across the grid. In this report they did some more interesting data analysis. This shows two of the graphs that you can find in this report. On this graph they compare mid-size battery electric vehicles and full-size battery electric vehicles with their full-size gasoline and mid-size gasoline cousins. in terms of global warming emissions. So this shows here that with electric vehicles, on average in the United States, you can achieve a reduction of more than 50% of global warming emissions for the same miles driven. It's interesting to note that the emissions that are coming from the manufacturing process are initially higher for the electrical vehicles compared to the gasoline vehicles. The battery, this is the blue part here, makes a big difference. And of course, for bigger cars, you need a much bigger battery, and so the energy cost or the global warming emissions cost for the battery goes up for bigger vehicles. But this is more than compensated by the much lower global warming emissions over the lifetime of the vehicles. The graph on the right here summarizes the data we saw on the map, and it compares electric vehicles depending on whether you are in a high carbon emission or in a low carbon emission state with gasoline vehicles. This data here came from the grids in Kansas or Colorado, and here the best value came from the upstate New York grid. And so you see, if you would move from Kansas to upstate New York, you could improve your greenhouse gas emissions by another 81%. Whether electric cars make sense under the current fossil fuel-based electricity generation, that can be discussed further, but there are other advantages to electric cars that deserve consideration. When you look into performance of electric motors, they have distinct advantages over gasoline engines. And one of the most striking advantages is the torque curve of electric motors. Electric motors have their maximum torque at 0 RPM, and that means that when you need to accelerate at a red light or so, you get maximum force, maximum torque to the wheels, and of course that is very desirable. If you compare that with a gasoline engine, the torque is actually maximum at a very high RPM, here at this model at 5000 RPM. If you've ever driven a car with stick shift, then you know that if you let out the clutch too early, the engine stops, and the reason for that is that the torque is very low in the low RPM range, so you have to rev up the engine and then let the clutch out in order to get the car going. In an electrical car, in contrast, all you would have to do is turn on the electricity, no clutch necessary, and the motor would start spinning at the highest torque when it needs to. So that's a really nice performance enhancement in electric cars compared to gasoline cars. Other advantages of electric motors are that they have a larger RPM range typically, and also that they are much more compact. And this reduces the need for transmissions, and four-wheel drive becomes, for example, possible with individual electric motors in each of the wheels. So as a bottom line, the electric motor is just a more advanced motor compared to a gasoline engine, and it makes sense to develop this technology, if not for energy savings, but definitely for performance. Now, if one thinks about the future, electrical energy will become more prevalent because photovoltaics and wind and so forth are increasing their share of the energy market. So it is a good idea to have the electric car technology ready and available when electricity will become the main energy source. Let's summarize the car section of this segment. Transportation on roads is a major energy use factor in the US. We are especially good at it because our cars have such a poor gas mileage, which is about 50% of that of other industrialized nations. In general, combustion engines have about a 25% efficiency for converting heat to mechanical work. So most of the energy in the gasoline is just emitted as heat into the environment. The energy goes into air drag, rolling resistance, and acceleration and braking. And of course, smaller and lighter cars would strongly reduce the energy needs per distance. When it comes to internal combustion engines, diesel engines are more efficient than gasoline engines, but we need to keep in mind that there is only a limited supply of diesel, and that means that gasoline cars are necessary to balance the consumption of the two fuel types. The recent advent of electrical cars has many advantages, but the environmental benefits and energy savings still strongly differ depending on where the cars are charged due to the different energy mixes in each of the electrical grids in the United States.
This concludes part 1 of the transportation segment. Thanks for watching.